All right, we had just talked about before the idea of accuracy and precision when it comes to measurements. So real quick review, right? Accuracy means that your measurements are close to the accepted value, which means they're right. And then you have precision, which means your measurements are close to each other, which means you're being consistent. So we said if you want to measure accuracy, if you want to judge the accuracy of something, you have to look at the percent error of it. If you want to judge the precision, though, it all deals with something called significant figures. Again, this is probably something that you haven't touched in other science classes or math classes, but it turns out that it actually is really important when you're talking about doing measurements. And since science is filled with times of doing measurements, then main significant figures turns out to be actually a pretty important concept. So let's go through and talk about what significant figures really means. So we know that precision, being consistent in your measuring, is limited by what tools you use to do the measurement with. I mean, everything you do measuring with requires a tool, right? So if you want to measure length, you might need a ruler or a tape measure. If you measure the mass of something, you're going to need like a balance or a scale of some kind. If you're going to measure the temperature of something, you're going to need some kind of thermometer. And it depends on how good the thermometer is, or how good the ruler is, or how small the measurement units are on it, or whatever it is. It's limited by the tools you use. So when we say how many significant figures are in a measurement, we're talking about all of the digits that are actually printed on the measuring device plus one estimated digit. So we're going to go through and kind of talk about what exactly that means. And so we'll use this as our first example. So we have this thing, this gray thing. I don't know what it is. It doesn't really matter what it is. Okay. Let's say that we're measuring the length of this gray thing. And we hold up this centimeter ruler to it. And we want to know how many centimeters in length is this thing. Now, when you look at this, the first thing that we do is we look at what whole number of centimeters is it past, right? And we can tell that this thing right here is definitely way past the 11, but it's not to the 12 yet. So nobody in the world could dispute that this is at least 11 centimeters long. Next, we can also see that there are these little lines posted on here, right? These little lines posted on here that must be the tenths, because there are 10 between 11 and 12. Right? So there's 10 little marks all the way to 12. And that means these are tenths of a centimeter, also known as millimeters, by the way. We'll get into that. So how many tenths of a centimeter is this past? And I think everyone would clearly agree that it's past the 0.6 mark, but it's not all the way to the 0.7 mark yet. So right now, I don't think there can be any discussion at all as to the fact that this is at least 11.6 centimeters long. But it's not right on the 11.6. So in our definition, we say that we always have to read one estimated digit past what's printed on here. And since these tenths are printed on here, that means the next digit past tenths would be hundredths, right? So at the hundredths place, I want to know how many hundredths do you think that is? Now, they're not printed on there, so this is an estimation. So what I want you to do is I want you to imagine between 11.6 and 11.7, if there were 10 more little tiny marks in between here, how many of those marks do you think it would have gotten past? Okay. So again, we know that it's clearly past the 11, and it's clearly past the 11.6, but we can't stop there. We have to estimate one last digit. So again, I want you to look at this and I want you to tell me, where do you think this falls? Do you think that's 11.65? Do you think that's 11.64? Now, everybody's going to be slightly different. When I look at that, I think that's 11.64. Okay, and that's what that looks like to me. You might say that it's 11.65, or maybe you think that's 11.63. So that's why I always give, when I say that I would call it 11.64, if this were like a quiz or a test and I asked you to measure this, I would give you a little bit of leeway on that last digit. All right, the 11.6 is without question, but the last digit is estimated, so everybody can be off by a slight amount. Okay? So this is what we mean by significant figures when you're measuring. You must measure so that you include all the digits that are printed on the device plus one estimated digit past that. So everybody does it the same way. Doesn't matter where you're measuring, what country you're from, what kinds of tools you're using to measure with. So every time I were to use this ruler, every time I would have to go to the hundredths place. What if, let me give you a couple of examples here. What if this weird gray thing that I'm measuring here turned out to line up directly with the 11.6 mark here? If it was right on the 11.6 mark, right, what would I say? Can I just say 11.6 then? No, because I always have to go to the hundredths place. Even if it's right on the 11.6, I would then have to say that it's 11.60. And I have to include that 0. Why? Because this ruler could have been 11.61 or 2 or 3 or 4 or 5 or something like that. And I have to let somebody know that it's right on the 11.6. I didn't just sort of guess that it was 11.6. It was 11.60 right on it. What if this gray thing were right on the 11 mark? I mean, like right on the 11 mark. What would I have to put down? Again, I have to go to the hundredths place because the tenths are printed on here. And I have to let somebody know I could have estimated all the way to the hundredths place. I would have to write down 11.00. And yes, those zeros would be important in this case. So if you really understand when you're using a measuring device how many places you have to go, then nobody is ever going to have the question, how far do I have to read this to? Right? That's never a question because there is a rule that everybody follows when they measure. All right, so let's try this with something different. We just used a ruler. Now let's use a graduated cylinder. So you can see in this picture we have a graduated cylinder. I don't know if it's water or not. It doesn't really matter. There's some clear liquid in there. And you can see that this clear liquid has this sort of inverted bubble to it. Right? There's an inverted bubble to it. That inverted bubble there is called the meniscus. Okay? So we always read where the bottom of the meniscus is. So right where this is where I need to do my reading. Okay? Now, we have some lines on here. These are milliliters. So this big line here that's marked 6, that's the 6 milliliter line. This is the 8 milliliter line. Where would 7 be? Yeah, hopefully you figured that out, right? It's this slightly longer line here. That's the 7 milliliter line. So then how much are each of these lines worth? Because there's not 10 of them between 6 and 7. There's not 10 of them between 7 and 8. So how many of those lines are there? Well, you notice there's 5, right? There's always 5 lines. And so if you split a milliliter up into 5 parts, each part would be 0.2, right? It would be 2/10. So each of those lines is 2/10. So let's do our readings here. So this is 6. So that means this is 6.2, 6.4, 6.6, 6.8, 7, right? So where does that line, that meniscus, fall? Well, it's clearly at or above the 6.6 line, right? In fact, I think it's a little bit above it, right? But it is clearly not to the 6.8. So what do we have to write down? Well, since the 2/10 lines are marked on this, that means the next digit past 2/10 would be 1/10. That means that I can estimate what nearest tenth do I think this is near. Since it's above 6.6, but it's not quite to 6.8 yet, I would call this 6.7. Now, if you think that's directly on the 6.6 line, I would have no problem with that if you called that 6.6 milliliters. The key here is that you realize this graduated cylinder, since it has 2/10 marked on there, then you must read to the nearest 1/10 every time. If that meniscus was right on the 7 mark, you would have to write down 7.0, not just 7. Here's an example of a triple bead balance. Right, you've probably used one of these at some point in science, but even if you haven't, it's a really easy device, right? So I want to measure the mass of something. These would be in grams. And so you notice this thing has a weight that sits on the 300. There's one that sits on the 70, so that's 370. And then this little one here has passed the 3, so that's 373. And so that means that there's 10 marks here between the 3 and the 4. So those are tenths. So we have 373.1, 0.2, 0.3. And notice where this guy is right here. I don't know how big your screen is or how well you can see that, okay? But that little mark there is past the 373.3. And that means I have to estimate what's past tenths? Hundredths. So I have to estimate to the nearest hundredths place. So again, I have to estimate how far between 373.3 and 373.4 am I. Now that doesn't look like it's quite halfway to me. So I would say that's 373.34. If you had said it was 373.33 or 373.35 grams, I would be fine with that. Again, it's an estimation. As long as you're close, you're good. But the 373.3 part is not negotiable. Everybody should be able to get that with no problem. And that means that since this balance has tenths of a gram marked on it, you must go to the hundredths place every time. If the item had been put on this scale and you had moved this and it balanced out, let's say, right at the 3 mark, that means you would have to write down 373.00. So you have to go to the hundredths place every time on that device. Okay? So when we do measurements, we know how far we have to measure. That's the significant figures of measuring. But what if you weren't the one that did the actual measuring? What if somebody just simply gave you measurements on a page? Like, for instance, what you're going to see a lot when you do problems in chemistry. Somebody's just going to tell you, oh yeah, there's 3.73 grams. So how do you know how many of those digits that they gave you are significant and which ones can you ignore? Or a better way of saying it, if they give you zeros, do you have to keep them all? That's what this is all about. So there are rules for recognizing significant figures in measurements. First rule is really simple. If it's not a 0, it's significant. In other words, you can't just drop it or ignore it. So we say that if somebody were to tell you 72.3 grams, the 7, the 2, and the 3 are all really important. You can't just round it off to 72, for instance. That's 3 significant figures, or sig figs as sometimes we like to call them. Now, what about zeros? Well, if you have a measurement that has zeros that fall between non-zero numbers, then those zeros are also important and we can't ignore those. So if somebody said there was 60.5 grams, well, you can't ignore that 0 because if you take that 0 out, it becomes a completely different number. So it's really hard to ignore zeros that are between non-zero numbers. So those are always significant. All right, so again, that would be 3 significant figures. If the zeros are to the right of the non-zero numbers, the significant numbers, and there's a decimal point in the number, then those zeros count as significant. So for instance, if I had 100.00, all 4 zeros there are important. Why? because there's a decimal point in that number. And so somebody was trying to tell you that they put those zeros there for a reason. There must have been some device that required them to read to the hundredths place, therefore you have to keep to the hundredths place also. If there's any other zeros that I didn't mention in the other rules here, then they are just placeholders and they are not significant. So let me give you some examples. If you had the number 0.0253, now why would somebody put the zeros at the beginning of that number there? It wasn't because their device required it. It was because they needed to show you what the number was by putting some placeholders in. You could have rewritten that number in scientific notation and not used those zeros. Therefore, there's only 3 significant figures. So again, another way of stating that is if the zeros are at the beginning of the number. So if you have zeros at the beginning of a number, they are never significant. They are simply placeholders and you can ignore them every single time. Now, if zeros are at the end of the number and there's no decimal point showing, like in 43,200, and there's no decimal point here at the end, that means those zeros are also just placeholders and you can ignore them. So if you were to rewrite this in scientific notation, those zeros would just simply drop off. They would not, however, in this case, you'd have to leave all 4 zeros on your number, no matter what you did with it. But if there's no decimal point showing, the numbers at the end of the number, or the zeros at the end of the number, I should say, do not count. Okay? Now, there's one more rule. We'll go through that in just a minute. But I want to point out before I get off of this that really there's 4 rules listed here. There's really only one that you need to remember. As long as you remember this last rule here, then all of the other ones won't really matter. Because it's easiest to remember, when are zeros not significant? Because there's only 2 cases where they're not significant. Otherwise, every other number you ever come across is. Zeros that are at the beginning of the number are never significant, and zeros that are at the end of the number are never significant as long as there's no decimal point. Those are the 2 rules you really need to know. All of the other rules are just telling you when things are significant, and that's easy. I said there was one last rule. The last rule is if we're using a number that is not a measurement, then that number doesn't have sig figs. In fact, we just say that they have an infinite number of significant figures. So if somebody were to say 6 molecules, well, that means they just counted 6 molecules. Nobody measured that. All right. So if you're not measuring, if you're just counting something, then that's not just one significant figure. That's an infinite number of significant figures. This also works for definitions. If somebody said there's 60 seconds in a minute, well, nobody had to measure that. Nobody had to go around with a stopwatch and measure how long a minute was. We know that. It's a definition. So you don't have to look at those numbers and go, oh, this is just one significant figure. Oh, this is one significant figure. No, it's an infinite number of significant figures. All right, let's try this. I'm going to do a few of these, see if you can get them. 508.0 liters. How many of those numbers there are significant? Well, we know the 5 and the 8 are for sure. Okay? So you just have to look at zeros and determine. Now, this 0 is in the middle of non-zero numbers, therefore it has to count. This 0 is at the end and there's a decimal point showing, therefore this 0 must also count. So how many is that? That's 4 significant figures. All right, let's try another one. So we have 820,400.0. Once again, I don't have to worry about the 8, the 2, the 4. Those are automatic. This 0 here is between the 2 and the 4, so it must automatically count. The last 3 zeros are all at the end, but since there's a decimal point showing, that means they actually have to count also. So that's a total of 7 significant figures. All of them are important. All right. For the next several, here's what I want you to do. I want you to try to do some of these on your own. So the next several, I'm going to pop it up. You pause it, try it out, then I'll tell you what the answer is. Right? That's the best way to learn these, is you got to try it yourself. Hey, if you get them wrong, that's all right. You're going to learn something from that. And if you get them right, then you really know that you know what you're doing. So try this one, and then I'll come back and show you the answer. Okay, so this one is written in scientific notation. Now, here's the deal about this part of it. The times 10 to the 5th is just telling you how many decimal places that decimal point was moved. So that's technically not part of the measurement. That is just telling you where the decimal point has to go. So the only part of the measurement you have to look at is here. And since there's a decimal point, that means that all the zeros all the way along all have to count. So that's 5 significant figures. All right, try this one on your own. All right, so you tried it on your own. Let's look at it. 807,000 kilograms. The 8, the 0, the 7, of course, count. What about those last 3 zeros? Do they count? No decimal point showing at the end. Therefore, they do not count. Remember, zeros at the end only count if there's a decimal point showing. There's no decimal point showing at the end. Therefore, there's only 3 significant figures in this number. Try this one. All right, what did you get? Did you get 5? Because you remembered that the zeros at the beginning of a number, even with a decimal point, the zeros at the beginning of a number never, ever, 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 ever count. All right, there is not a scenario where the zeros at the beginning count. But the 0 at the end counts because there is a decimal point. So we have the 4, 9, 4, 5, 0 are all significant. So then what about this one? Did you get that one figured out? So we have these zeros are all at the beginning of the number. It doesn't matter if there's a decimal. The zeros at the beginning never count, so only the 4, 8, 2 count. That's 3 significant figures. How about this one? This one's easy. This one's easy. Remember, I just said before that this is just telling us where our decimal point goes. We don't have to worry about that. The only thing you have to worry about is this part of the number. And of course, all of those count. None of them are even zeros anyway. So there's 5 significant figures. What about this one? By now, hopefully you're getting it. Now you know there's a decimal point here, but that doesn't matter because these zeros are all at the beginning of the number. And they're not at the end of the numbers. They never count. So that's just 2 sig figs. All right, we have 2 more. How about this one? So, did you count all of them this time? You had to count all of them. These zeros here, these zeros are between the non-zero numbers, so they automatically have to count. And these zeros are at the end of the number, and there's a decimal point showing, therefore they all have to count. This is all 11 of them are significant. All right, how about this one? Does it seem easy to you? That's probably because you forgot rule number 5 at the top there. 8,500 chickens. Chickens is not a measurement. You're just counting them. Therefore, that's an infinite number of significant figures. You don't even have to pay attention to those numbers. Those numbers are not going to be a big deal to us. If you count something, you're not measuring, you're counting, then it's an infinite number of significant figures and you don't have to worry about it, okay? All right, last thing with significant figures. Once you identify significant figures, then we have to use that when we maybe have to do something mathematical with those measurements. So using sig figs mathematically, first thing I want to kind of go over with you, or review more than anything else, is rounding. You guys have done rounding in math before. When we round measurements, we're doing the same thing that you would have done with regular rounding, except you're going to have to think about your significant figures. So for instance, let's say that you were given a measurement of 84,791 kilograms. But you needed to round that off so it were only 3 significant figures. Now, how many significant figures are in it right now in its current form? Well, there's 5. 8, 4, 7, 9, 1, all count. Now, if I want to round this off, if I round this off, right, and still keep it close, because rounding just simply means you go to the next closest number. So what's the next closest number to 84,791? Well, 84,792 might be close, or 84,790 would also be close. If I wrote this as 84,790, the 0 at the end wouldn't count anymore, right? There's no decimal point showing. So now I would be down to 8479. So I'd be down to 4 sig figs, but I want to get to 3 sig figs. So what's the closest number to 84,791 that only has 3 significant figures? Well, what about 84,800? Right? 791 is close to 800. So 84,800, you'd have 2 zeros at the end. There's no decimal point showing. And the 848 would be our only significant figures. So it's a number that is pretty close to that number, but it only has 3 sig figs in it instead. Now, we had a rule we talked about with scientific notation. We said that if it's greater than 1,000, we have to write our answer in scientific notation. So if you took 84,800 and this invisible decimal point down here, you moved it over so it's a number between 1 and 10. 1, 2, 3, 4. That would give you, what, 8.48 times 10. That's a really horrible 8 there. 8.48 times 10 to the, how many places do we move it? 4. All right, so 8.48 times 10 to the 4th is what that should be rounded to. Let's try another one. 38.5432 grams. I want to round that off, however, to just 2 significant figures. Well, look at this. Right now, how many significant figures is that? That's 6 significant figures. But I only want 2 significant figures. But I have to stay close to this number. So what number is closest to 38.5432 that only has 2 significant figures in it? What about 38.543? No. 38.54? No. What about 38.5? No. Well, if I round 38.5 to the nearest whole number, what is 38.5 closer to, 38 or 39? That's a little closer to 39. So I would round this off to 39 instead. Only has 2 significant figures to it, and it's basically the same number you had before. Now, do I have to write 39 in scientific notation? Is it bigger than 1,000 or less than 1,000? No. So I can just write that as 39. How about this one? This one sometimes gets people, but you can do it. I want to round 256.75 centimeters off to 1 significant figure. Right now there's 5 significant figures in here. I only want to round it off to just 1. So 256.8? No, that's still too many. What about 257? No, that's still too many. What about 260? No, that's still too many. Well, what could you round 260 to? What's it closest to that only has 1 sig fig? What about 300? All right. 256 is somewhat close to 300 because 300 only has 1 significant figure. I wouldn't count the zeros at the end. There's no decimal point showing in the number 300. And again, I don't have to write 300 in scientific notation. It's not big enough. You can if you want to, but you don't have to. All right, try this last one on your own. And again, pause and come back and I'll show you how to do it. Okay, you've tried this one on your own. So we've got 2 significant figures here. I want to get to two significant figures. Right now, we have the 5, the 4, the 8, the 1, and the 8 all count. Remember the zeros at the beginning never count. So already they don't count anyways. But I can't just drop off, let's say, all of this. That would make no sense. If I dropped off all of that, then I would be left with 0.00. So the easiest way to do this is to write this in scientific notation. If we write this in scientific notation, then we can do it. So let me take and get rid of that line so we can work with this. All right, if we write this in scientific notation, I would move this over 1, 2, 3, 4 spots, right? So now this would be 5.4818 times 10 to the -4th, right? Except, again, this is still too many significant figures. There's 5 significant figures here. I only want 2. So I just need the 5 and then whatever number this would end up being closest to. And since there's an 8 next to the 4 would round up to a 5, right? So in the end, this should just be 5.5 times 10 to the -4th. So, oh, I've got one more. Try this one. If you remember, the 3 zeros at the end here don't count. There's no decimal point showing. But it's still way too many significant figures. I want to get it down to 3. Once again, since this is a really big number, I recommend writing in scientific notation first. You're going to have to do it for your answer anyways. So move it over 1, 2, 3, 4, 5, 6, 7, 8 places, right? I'm going to move it over 8 places, but again, I only want to keep 3 of the significant figures. So I can keep the 3, the 0, and I'll leave this as an 8 because there's a 4 next to it. So the 8 would stay an 8. So I just need the 3, the 0, the 8, and then times 10 to the, how many places did I just move it? 8 places. Okay. Now, let's talk about what happens when you mathematically take measurements and you have to add or subtract them together. Okay. Here's the rule. The rule is when you're adding or subtracting measurements, the final answer can have no more decimal places than the least number of decimal places in the problem. So I want to take 258.3 kilograms and I want to add it to 257.11 kilograms, and then I want to add that to 253 kilograms. So if I have all 3 of these measurements and I want to add them together, it's obvious that they didn't come from the same balance. This balance only required to go to the tenths, this balance required to go to the hundredths place, and this balance can only go to the nearest whole kilogram. So I'm using 3 completely different balances. Which balance can you measure the most precisely with? Well, obviously this one that goes to the hundredths place. What's the least precise, however? Well, it's this one that has no decimal places. So it turns out that I need to make sure that my answer is no more precise than the least precise measurement that I used in my problem. 253 has no decimal places. So even though if I were to plug this into my calculator would tell me 768.41 is the answer, I would know that, hey, 253 was the least precise measurements, means no decimal places can be in my answer. So I'd have to round that off to just 768. So anytime you add or subtract, you're looking for what's the least number of decimal places in the problem, and that's what you round off your answer to. Now, multiplying and dividing is a little different. Multiplying and dividing, the final answer must have no more significant figures total than the least number of significant figures in the problem. So now I'm not just looking at the decimal places. I'm looking at all of the significant figures. So I wanted to multiply these 3 measurements. So I have 2,010 centimeters times 15.2 centimeters times 1.858 centimeters. So this first measurement here has 3 significant figures. Right? The 0 doesn't count here at the end because there's no decimal point shown. This one also has 3 significant figures. This one, however, has 4. So that means that the least number of significant figures in this problem is 3. So my answer can only have 3. But if you plug this into your calculator, this is what your calculator is going to tell you the answer is. Your calculator does not know significant figure rules. So you're going to have to apply this yourself. You're going to have to look at this answer when you're done and say, well, I can't write that as my answer. I can only use 3 significant figures of my answer. So I have to take this and round it off to 3 significant figures, and that would be the answer. So this is really key. Anytime you're doing any kind of math problem with measurements in this class, and we will be doing this quite often, then you need to make sure that your answer follows these significant figures rules. At no time should you ever have to ask me, how many places do I have to write down off my calculator? You already know what the rule to that is. You know how many places you have to write down. That is the key.